Welcome back. I'm glad you decided to join me for part 2 of the Unit 3 test prep video. Your test scores will thank you for it. Now we want to graph y equals negative x squared plus 3. And we need to determine whether it's a relation or a function and determine its domain and range. We've got a xy table here. We're given some x values. So all we got to do is plug them into our function to find out the corresponding y values. So if x is negative 3, negative 3 squared is 9, but I still have this negative sign out front. So negative 9 plus 3 is negative 6. That gives us the ordered pair negative 3, negative 6. Starting from the origin, negative 3 on the x means left 1, 2, 3. Negative 6 on the y means down 1, 2, 3, 4, 5, 6. And there is our point. And there's our label. Let me clear my ink and let's see what happens when x is negative 2. Negative 2 squared is 4, but I still have the negative out front, so negative 4 plus 3 is negative 1. This gives us the ordered pair negative 2, negative 1. Negative 2 on the x, always start at the origin. Negative 2 on the x is 2 to the left. Negative 1 on the y is down 1. So there's our next point and our next label. When x is negative 1. Negative 1 squared is 1, but we still have the negative sign out front. Plus 3. Negative 1 plus 3 is 2. So negative 1, 2 is our next ordered pair. Negative 1 on the x, up 2 on the y. There's that. And when x is 0, 0 squared is 0. 0 plus 3 is 3. So 0, 3 is our next point. Over 0, up 1, 2, 3. When x is 1, 1 squared is 1, but the negative's still there. Plus 3. Negative 1 plus 3 is 2. So our next point is 1, 2. Our point and our label will show up there. When x is 2. 2 squared is 4. Still got the negative. Plus 3. Negative 4 plus 3 is negative 1. So our next point is 2, negative 1. Over 2 to the right and down 1. And here comes our label. And when x is 3, 3 squared is 9. Negative still out front. Plus 3, that's negative 6. 3 negative 6 is 1, 2, 3 to the right, down 6. Label that point. And next, we're going to draw a nice smooth curve through all these points. I am such a good artist, aren't I? Okay. Now, is this relation a function? We can use this vertical line test to determine whether it's a function. And all we do is we pass the vertical line over the graph and see if it's ever touching the graph in 2 spots at once. So as it passes through, it looks like it's only touching 1 spot at a time. Follow it through. Whoa, only touching 1 spot at a time. So as long as it's not touching, as long as this purple line is not touching the graph in 2 spots at once, it's a function. So this graph represents a function because no vertical line intersects the graph in 2 places at once. That means that there's no input value that gives you 2 different output values. So for each input, there's only 1 output. All right, how about domain? So the domain is asking about what x values does this function cover. And this function goes all the way to the left. This keeps going down and to the left forever. And it also goes down and to the right forever. So there is no x value that this function doesn't cover. And it kind of makes sense that you can put any number in for x and square it. You're allowed to do that. So the domain is all real numbers. But the range, this function starts up here. It has a highest point, and then it covers all the y values down below this point, but it doesn't cover any y values up here. And this point here was 0, 3. So the highest y value that it attains is 3. But it covers every y value below that. So the range is y less than or equal to 3. And you may have seen this kind of set notation here. A set of all y such that y is less than or equal to 3. Let's tell whether each of these functions is or each of these graphs represents a function or not a function, linear or nonlinear, one-to-one or many-to-one, increasing or decreasing. And if it increases and decreases, what intervals does it increase and decrease over? Well, first, to check if it's a function or not, we use the vertical line test. So we're going to watch this vertical line pass over the graph, and if it never touches the graph in two spots at the same time, then it's a function. So it looks like it's only ever touching the graph in one point at a time. So that is a function. All right, is this a linear or a nonlinear function? Well, that's just asking, is it a line or is it not a line? And this is a line, so the function is linear. Is it one-to-one or many-to-one? We answer this by doing the horizontal line test. As the horizontal line moves down the graph, if it's only touching in one point at a time, then it's one-to-one. If there's ever a spot where this purple line touches the graph twice at the same time, then it would be many-to-one. This one's only touching at one point at a time, so this one is a one-to-one function. Is it increasing or decreasing? Well, as we move to the right, this function is always going down, so this function is always decreasing. How about this one? Function or not a function? Let's check the vertical line test. Each vertical line is only intercepting this graph at one point at a time. So that is a function. Is it linear or nonlinear? Well, it's not a straight line. It's curvy, so it's nonlinear. Is it one-to-one? Horizontal line test. Does the horizontal line ever touch the graph in two spots at once? No, there's no horizontal line that touches the graph in two spots. So this function is one-to-one. Is it increasing or decreasing? As we move from left to right, the function is always going down. So this function is decreasing. What about this guy? Function or not a function? Vertical line test. As the vertical line moves across the graph, it's only ever touching the graph in one point at a time. So this is a function. Is it a line? No, it's curvy. So it is nonlinear. Is it one-to-one or many-to-one? That's the horizontal line test. Now you can already kind of see the line is touching here and here. So there's two spots. Two spots at a time. And looky here. 1, 2, 3, 4 spots at a time. So that means that this is a many-to-one function. Is it increasing or decreasing? Well, as I go from left to right, it's decreasing here, and then, uh-oh, it's increasing here. Oh, now it's decreasing again. And, oh, it's increasing again. So where is it decreasing? Decreasing here. Then it's increasing, and now it's decreasing again here. So what intervals are those? It looks like less than 1, and then between 0 and 1. So we can say that like this. The function is decreasing when x is less than -1, and when x is greater than 0 but less than 1. Well, where is it increasing then? It's increasing here and here. So it's increasing from -1 to 0, and it's increasing from 1 and up. So we can say that function is increasing when x is between -1 and 0, and when x is greater than 1. How about this function? Or is it a function? Let's find out. Vertical line test. Only touching 1 point at a time. 1 point at a time. Yeah, that's a function, all right. Is it linear? Is it a straight line? No, it's curving, so it is non-linear. Is it 1-to-1 or many-to-1? That would be the horizontal line test. Is it touching the graph in more than one spot at a time? No, there's no horizontal line that touches the red graph in 2 spots at once. So this is a 1-to-1 function. And as you move from left to right, this function is always going up. So this function is increasing. So we're going to look at these 2 sequences and learn about them. The first one is 2, 4, 8, 16, 32, 64, 128. And it looks like we're multiplying by 2 each time. The second one is 8, 16, 24, 32, 40, and it looks like we're adding 8 each time. So describe the pattern in each sequence. Sequence A, each term is 2 times the previous term. And in sequence B, each term is 8 more than the previous term. So what's the next number in each sequence? Sequence A, the last number was 128, so we're going to multiply by 2. 128 times 2 is 256. For sequence B, the last number is 40, and we just need to add 8 to get the next term. So that's 48. So what kind of sequences are these? Sequence A has a common ratio. We multiply by 2 each time. So that's a geometric sequence. Sequence B has a common difference. We're adding 8 each time. So that's an arithmetic sequence. Now we're going to create a sequence and plot some points and sketch a graph of a function that demonstrates exponential growth. If I start on day 1 with $1 and I double my money every day, it goes like this. I got $1 on day 1. Day 2, I have $2. Day 3, I have $4. Day 4, I have $8. Day 5, I have $16. I like the way this is going. Let's graph some points. On day 1, I have $1. On day 2, I have $2. On day 3, I have $4. And on day 4, I have $8, which is like so many dollars that I'm not even on the graph anymore. And then draw a little curve through there, and that demonstrates exponential growth. It's truly been a hoot. I hope you have a great time taking this test. See you soon. Bye-bye.